So we've been talking about ethers and epoxides, but we're taking a detour, what's going to feel like a detour for a quick minute, to jump to Chapter 11 and a couple of reactions in Chapter 11. Then we'll circle back around, and I think you'll understand why we took this detour. In all of the reactions we've learned so far, carbon has been an electrophile. Carbon is typically an electrophile. Carbon is typically connected to something more electronegative than it, like a halogen, like an oxygen, like a nitrogen, like all kinds of things in those functional groups we've been talking about, substitutions and eliminations of. When carbon's connected to something more electronegative, it makes the carbon partially positive. So when a nucleophile comes, it can attack the partially positive carbon because that carbon is an electrophile. But carbon can be a nucleophile. The way that carbon can be a nucleophile is if carbon is connected to something less electronegative than it. That points the dipole the other direction versus the top example, making that carbon partially negative, and partial negative leads to that carbon being a nucleophile. So that nucleophile can then attack other electrophilic things. The reason this is given an M is because a lot of times carbon can be connected to certain metals, and all metals are less electronegative than carbon. So we'll see carbon connected to a lot of metals in Chapter 11. One of the most common metals that carbon gets connected to is magnesium. Magnesium is less electronegative than carbon, so there's a dipole pointed toward the carbon. That makes magnesium partially positive, carbon partially negative. Lithium, definitely less electronegative. That makes lithium partially positive, carbon partially negative. It doesn't matter what metal it's connected to. In all of these examples, the metal is less electronegative than carbon, so the dipole points toward carbon, making the carbon partially negative and the carbon nucleophilic. All of these kind of things where carbon is connected to a metal are called organometallics. Carbons and metals are close enough in electronegativity to share electrons a little bit. Does oxygen and lithium share electrons? No. They're too different in electronegativity. But carbon is close enough in electronegativity Carbon is close enough in electronegativity to actually share some electrons between carbon and metals. But the less electronegative the metal is, the more ionic character that bond has. So, of all these metals, lithium is the least electronegative of these metal examples here. Lithium is the least electronegative, which means this carbon-lithium bond is most ionic. Is it ionic? No, it's officially sharing like a covalent bond, but it's closest to being an ionic bond. The next least electronegative is magnesium. So this is next most ionic. I know that's a weird way to say that. I know, I got it. That means that those two organometallics are more reactive than any of the other organometallics. Because lithium is least electronegative, that is the number one most reactive organometallic, and then magnesium is next. Those are the two most common organometallics, period. But there really are a lot of them that we will see. There's even an upper-level chemistry class all about organometallics. It's a very wide, big area of study, and they're very flexible compounds. We're going to only be exposed to the bare surface of what these things can do. Organometallics that are organomagnesiums are called Grignard reagents. We will talk about them as Grignard reagents a lot. Organomagnesiums, Grignards. Okay. How do you make these organometallics? Well, we're going to focus most specifically on those two that are the most reactive, but we will talk about those others later in our Unit 2 stuff. But we start out with an alkyl halide. It does not matter what kind of halide. This is an aryl halide. It doesn't matter. Start with an alkyl halide and add a solid metal. This is magnesium solid metal. Sometimes you will see it written with a little 0 up top. That's telling you it's a magnesium with 0 charge. It's a magnesium with 2 electrons. You'll see a little lithium 0 sometimes. A lithium with 0 charge. It's not a lithium plus. It's a metal lithium, a metal magnesium. What happens between these things is a radical reaction. And we won't draw those arrows. It actually is in your book. You can look at it if you want to. But what happens is magnesium squeezes itself between the carbon and the bromine, like so. And lithium simply takes the place of the bromine. What? How does this work? Well, magnesium, when it's ionic, it's a stable +2 charge. So that's why it sandwiches itself between the carbon and the bromine. Because it behaves, I'm putting this in quotes, it behaves like this kind of compound. It behaves like a carbon with a minus, a magnesium 2+, and a Br-, and it's all sandwiched together like the drawing that the computer made. That's a Grignard reagent. How do you make a Grignard? You add solid magnesium metal to an alkyl halide, and magnesium will squeeze itself between the carbon and the halogen, carbon and the Br. Lithium does the same thing. You get some lithium bromide salt as a side product, but because lithium itself is a +1 charge, that's why you don't squeeze bromine and lithium between like that. It behaves like a carbon with a minus and a lithium with a plus. They really are sharing electrons, carbon and these metals, but they behave like carbon with a minus. What do you know about carbon with a minus? Carbon with a minus is a super strong base. Super strong base. Carbon with a minus, really, really strong base. Grignard reagents are really, really strong bases. So if you have a Grignard reagent and something like water, all you do between these things is an acid-base reaction. You end up getting a hydrogen from your water connected to the carbon. Note my electrons came from between the carbon and the magnesium. The butt of my arrow is between carbon and magnesium. And I get a hydroxide, and I get a magnesium 2+, and I get a Br-. Because now that the carbon minus is gone, magnesium does not make covalent bonds with O or Br, so you get all that clutter, salt stuff. This is an alcohol. Grignard reagents definitely are strong enough to deprotonate an alcohol. So you get an O- out of that, and you get your Grignard. The MgBr is replaced with an H, and you got a magnesium salt and a Br salt. These reactions are not particularly useful because Grignard reagents are very special reagents. They're difficult to make in a lab, but they're very special reagents. You usually want to use them to do something more creative than simply deprotonating water or deprotonating an alcohol. You can use something a lot less creative than that. So instead of these deprotonation things, we usually want to do something else. When you want to do something else with your Grignard, you have to make sure that the solvent you use in your reaction has no hydrogen heteroatom bonds. Why does that matter? If you have hydrogen heteroatom bonds, the Grignard will simply act as a base and deprotonate your hydrogen heteroatom bond. The thing that you're trying to turn into a Grignard, like back here, this thing that you're trying to turn into a Grignard, it cannot have any hydrogen heteroatom bonds. That's a big deal as we move forward and talk more about these Grignard things. Grignards are strong bases. If you have any hydrogen heteroatom bonds, you're going to use your Grignard to deprotonate that thing again and again and again. In all of these examples, this bottom one is not a hydrogen heteroatom bond, but a terminal alkyne is kind of acidic. So in all of those, your Grignard, your CH3-MgBr, your CH3-MgBr, was simply used as a base, and this is the conjugate acid of that base. and you deprotonated all your hydrogen heteroatom things and your terminal alkyne in the end. They're not these reactions are not super useful. We really want to use our Grignard for something more useful. We're getting there. Bear with me. If you have an alkyl halide and you add magnesium to it, the magnesium will squeeze itself between the carbon and the Br. If you add regular water, you get regular butane. If you add deuterated water, you get a deuterium in the place of where that MgBr was. The way the curved arrows would look are like this. Yep, you add a deuterated water, you get a deuterium in place of the MgBr. So it can be useful if you're wanting a deuterium instead of a hydrogen. But other than that, all these acid-base Grignard reactions, not crazy useful. But one place where it is pretty useful is when you add a terminal alkyne like this. You can think of that as making CH4 and C minus. But now that we know that carbon is really technically capable of making a bond to magnesium, instead of seeing it as this C minus thing, we're much more likely to see it as carbon connected to an MgBr, like that. We're not drawing any curved arrows of how that MgBr got connected to here. We could only draw the curved arrows of how that hydrogen gets displaced, how that hydrogen gets plucked from that terminal alkyne. Yeah? So we get those two products. We have a brand new Grignard. We started with one Grignard, a methyl Grignard, and we ended up with an alkyne Grignard. Caution, note, this is how tricky multiple choice questions are assembled sometimes. Turning one Grignard into another Grignard and then using this Grignard to do something useful. Okay, that was a weird little hiatus we just went on talking about organometallics. But the reason we talked about that is because it's very, very, very common for organometallics to react with epoxides. Epoxides like this one. I'm going to change this one to be this epoxide. Maybe you'll forgive me. This epoxide, we put an ethyl leg on that methyl because I want two asymmetric carbons, like that. Grignards are super strong bases. So I attack the least substituted side and bust open that epoxide like so. From here, I get an O minus, a dash, a wedge. That wedge should be the ethyl because the ethyl did not get, that side did not get attacked. That side was not involved. So leave that side alone. If I point my benzene down, my epoxide let go from up top. It was pointed up in the plane. My benzene is pointed down in the plane. That means my methyl here should stay wedged. And a wedge there definitely shows inversion of configuration. Yep. Grignards themselves are super strong bases. So you cannot get a neutral product after you add a Grignard. You cannot. It's going to be this, and it's going to sit around as this in a flask until you add some acid. It's often considered acid workup. You don't know what it is quite yet because we've not done an organic lab, but that's often an acid extraction. So that O minus attacks the H plus of your acid to give you your alcohol product in the end. Grignards love to attack epoxides, and because they're bases, they attack on the least substituted side, and they still always and forever do SN2 reactions, and you get an inversion at the stereocenter, or at the center that was attacked. Yeah? Okay. The words on here say an alkoxide is produced. Alkoxide is this thing. That means the conjugate base of an alcohol. Because Grignards are strong bases, thou shalt not get an OH product when a Grignard attacks an epoxide. That alkoxide, it says, can then be hydrolyzed, acid workup, to produce an alcohol. That must be a separate step. If you were writing out this thing as a reaction conditions, you would write epoxide. We're going to squish it up here in the top, and maybe it's legible. Plus, number 1, add this Grignard thing, and let that Grignard thing do its own thing for a while. Then number 2, acid workup. Yeah. Separate steps. The acid and the Grignard shall not be combined together. It's kind of a big deal. All right. Grignards, we talked about how to make them. We got to remember how to make them. But Grignards can react with a ton of things. Aldehydes and ketones, that's unit 3. Esters and acid chlorides, that's unit 3. Carbon dioxides, that's unit 3. Nitriles, that's unit 3. All of these things will be covered in unit 3, but we're talking about how Grignards react with epoxides for now. Grignards and epoxides. Grignards are bases. Attack the least substitute side. Yeah? You got it? All right. That's ethers and epoxides, and that's all that those guys do. Okay.